So in total, I have 20 moves. So I'm going to assume that Alice always is going to start, and therefore Bob has the last move. Wait 2 seconds. Okay. Okay, so there are 2 moves, and for each of the players, and in each move there are 2 possibilities. Okay, so each player has 2 possibilities in each of them. Okay. Okay, regarding the outcome of the game, so the outcome of the game is determined for the exact sequence of moves of both players. What does it mean? Mean that you need to know exactly the full history of the 2 players to say what is the outcome of the game. So you can think in this game as a game in a binary tree. Okay, so I have here Alice, Bob, Alice, Bob. Okay, so I have in total 2n moves or 2n sequence that leads to a leaf, and therefore in total there are 2 to the power 2n possible outcomes. So in other words, this is the number of leaves in this tree, 2 to the power 2n possible outcomes. Okay. There is a delay, so I am ready. then you say Alice win. Oh. Okay.
Alguien que se quede ahí, alguien que se quede parado con el dedo ahí. Ahí adelante.
Okay, so I'm going to know. Okay, so I'm going to know by this P. So the probability that that lead is a 1, and this is the probability that Bob is winning for that lead. Okay, so in other words, I'm going to assign zeros and ones in IID way, so independently and identically distributed according to some random variables, and the intensity of this variable is P. So, okay, 0 means Alice win, 1 means Bob win. Sorry, I said other way around. Okay, 1 is for Bob. Okay, so in other words, Alice is going to minimize and Bob is going to maximize in each of the labels, in each of the levels of the tree. So the question is, what is the probability that Bob has a winning strategy? So that means that regardless of what Alice does, what is the probability that Bob has a winning strategy? So, for example, in this game, so I assign, sorry, in this tree, I assign 1 and zeros randomly, no? According to some Bernoulli's random.
Excuse me, I have a little question. Sorry, the players know which league are they're winning.
No, they don't know.
They don't know.
They don't know.
Okay.
But I assign these values here to the game, but they don't.
Okay.
So there are 2 ways to see this game. So there is the theoretical game way to see, and is then you start with a token in the root, and then the players start to move this token to one of the leads. So this is like the game view of the game, and the probabilistic way to see this game is backward. So you assign the values zeros and ones in the list, and then you propagate these values back to the root, and depending on the value of the root is the winner of the user of the game.
Yeah, just a brief question, just to follow what he was saying. So, does the player have some sort of strategy to decide which how to move, or it's just through randomness?
Yes, it's randomly, but when you see the game the other way around, so you assign these zeros and ones, then you do in this way, mix and match. So if they play optimum, then they are going to play min and max. These are the operations. Okay. Okay. It's not very difficult to see, but actually the probability that Bob has a winning strategy is equivalent that the probability, sorry, that the value of the root is equal to 1. Okay. Okay, so let me show you an example. So this is to see the game backward. So then you start with these zeros and ones in the lips, not that I assign, as I already said, according to some Bernoulli as random variables. And then Bob wants the final lip to be 1 in order to win. So then Bob is going to maximize these values. Okay, so then he takes the maximum of the values of the lips. Okay, then Alice, in her last move, she is going to take the minimum because she wants in the lip a C. Then she is going to take the minimums of the children. Okay, and then in the first move of Bob is going to take the maximum again. And then in the first move of Alice, Alice is going to play the minimum. So for this assignment, so what I get in the root is a 0. So that means that Alice is going to have a winning strategy. So that means that regardless of what Bob does in the game, if she plays optimal, she's going to win. Okay, she can guarantee it. Okay. So let me know by this P here, the probability that Bob has a winning strategy. Okay, I'm going to use this capital A, capital B, because this is the name that I will give to this game, because I'm going to introduce another. And N is the number of moves of each player does, and P is the probability of having a 1 in the lead. That is means winner for both. Okay, so then the question is, what can we say about this probability when we go deeper in the tree? No, when can we say when the number of moves increase? Is there a phase transition in P? Okay, so then for this game, it is so difficult, and we can actually deduce a recursive equation for this problem, because this is a binary tree and you have a lot of independence. You can actually construct a recursive equation. Okay, so remember that both maximize, Alice minimize, and then at the both vertex, the value is 1, since both maximize, if at least one of the two children is 1. Okay, and in an Alice vertex, the value is 1 only if both children are equal to 1, because she minimizes. Okay. So then using these two rules, so if I start P0 AB equal to P, so then this probability here, so Pn minus 1 ABP, so this is the probability of a winning for Bob. So then 1 minus P is Bob lose the game. 1 minus P2 squared means that I have 2 zeros, okay? And then 1 minus that means that at least I have 1, 1. That is what I need in that vertex for both has winning, okay, strategy. Okay, and then this is for both vertex, but remember that Alice precedes the game. So then for both in an Alice vertex, what I need to have is 2 1s, because she's going to minimize. So then this is why I have here this square. Okay. Okay, so then I have this function f here that is 1 minus x squared to the power 2. Okay, so then in order to understand this game when n goes to infinity, I need to understand this function. So in particular, I need to understand the fixed points of this function. No? So these points that doesn't change when n goes to infinity. So, and then we can compute the fixed point of that equation. And the fixed point of that equation are these 3 values, 0, 1, and this very beautiful number here. I don't know if you recognize, but okay, I will tell you later. So this 3 minus square of 5 over 2. These are the 3 values of that function. 3, 6 values. Okay, so this game was studied by Per in the 80s, and he showed the following. So when n goes to infinity, the probability that Bob has a winning strategy is going to go to 0 if you start below this critical value. So that means that if you start P less than this critical value, Alice is going to have a winning strategy with high probability if the number of moves is large. Okay. If you start the game with this P a little higher than this critical value, then Bob can guarantee victory with high probability when n is large. Okay. But what is interesting here is that if you start exactly at this critical value, you stay there. Okay, so in this critical value, then you don't have a trivial probability. No? So you start with that probability, and then this probability stay there when n goes to infinity. So, and this value has a very nice effect that actually 1 minus PC is the golden ratio. So, so this value here, you can see that this value is less than 1/2. So that means that there is an advantage for Bob. And this is because Bob has the last move. So having the last move in this game gives him an advantage. Okay, so I have here some pictures. So, so this is P here, and I have here the probability of a winning strategy, and each of these cubes correspond to different ends. So, for example, n equal to 0, so is the diagonal, n equal to 1 is this cube here, and then the highlighted cube correspond to n equal to 9. So that means that each of the two players move n times. Okay, and then you can see here that there is a sharp transition when n goes to infinity. Okay. Okay, so so let me say a few words about the literature. So there is this work by Pimental and Ward from 2006. So they study a model also in a binary tree, okay, but now the operations are taken random. So it's no mini, max. So instead, in each level, you decide randomly which operation you are going to apply. Okay. So there is also this other work by Martin Stanczynski from 2018, and they study also a mini-max game, but in random tree that is called Benami Galton Watson tree. So let's think that is a random tree, no? The number of edges is not fixed, so you decide in every generation how many are going to have according to rules. Okay, I won't enter to detail here. Okay, and this other work by Brotin and Mailan from 2022. So they also study a minimax game in another kind of random trees. Okay, so what we can see here is that all of these minimax games are in trees. Okay, so then the question is, what if the game is not a tree? So what if different game histories can lead to the same outcome? Okay, so this was one of the motivations that we had, and we studied the following modification of the game that I just introduced. So it's a simple modification. So what is the modification? So the rules are the same, except that now for the outcome of the game, so I need to know the full history for Alice, but for Bob, I only need to know how many times Bob played a particular one of the two moves. That's all what I need. So I don't need to know the full history. I only need to know how often he plays one of the two moves. Okay. Okay, so then how many possible outcomes do I have here? So I have 2n that are the possible outcomes that the tree of Alice give me. And then I have n+1 because Bob can play 0 times one of the two moves or can play n times one of the two moves. So in total, he can place n+1 possible moves. Okay, so then there are in total 2n times n+1 possible outcomes for this game. So there are less outcomes compared with the previous one. Okay, so this is an illustration of the game graph now. So it's a sort of product between a binary tree, okay, and n squared. So Alice is going to play in this kind of binary tree as before, okay, but Bob is going to play in n squared, no, in the positive integer lattice. Okay. So here, so then the graph is something like this. It's like a product. So I have here Alice, then I have Bob, then I have Alice, and then I have Bob. But then you can see that now different histories of the game can lead to the same outcome of the game. Okay, so then I don't have now independence. Okay, I'm losing a little bit independence with this game. So, but I'm allowing that different outcomes can lead to the same different histories can lead to the same outcome. Okay, this is another illustration, another projections of this graph. So for example, here in the left, so if you see the red, then you see the binary tree, okay? And then if you see the blue, so it's only some vertical lines. So this is like the point of view of Alice, okay? So you see the binary tree, and in between these blue vertical lines. And then if you see this one here, so this is, you see in blue now, the positive integer lattice, okay? And in red, you see the vertical lines, okay? This is the gain tree from the point of view of Bob, okay? And I have here another rotation of the gain graph. So this is for 3 moves for each of the players. Okay, so why it's interesting to do this? Why it's interesting to allow that different histories merge or lead to the same outcome? So okay, in this game that I introduced at the beginning, so every history leads to the distinct position in the game of the tree. And in the 80s now show that this minimass game can behave pathologically. So that means that looking further ahead can lead to worse decisions. And this is because the independence that you have. So every time that you go further, when you need to come back to the root. No? And then it behaves, so your decision is worse. No? That is something that is not very intuitive. Okay? And then in a paper in the 80s, he also showed that this pathology disappears when different histories can reach the same position. Okay? Because then, so when you are searching, when you are doing this exploration, you can reuse the analysis of some of the paths, no? Because then you have this history that lead to the same outcome, then you can reuse that information. Something that you don't have if you have independence or if you have a binary tree or a tree. Okay, this is one of the motivations that we have. Okay, so let me come back to the game. So of course, you can define different combinations of these games. So this one here, this notation is for the original one, so that the game graph is a 3 times 3. A, B, N, so this is the game here in this kind of product of this graph. So you, of course, you have the other way around. So you can ask that for Alice only matters how often she plays a move, and for Bob, all the history. And you, of course, you also have the other combination, okay? So let me know by this piece here with the superscript, the probability that Bob has a winning strategy in each of these games, okay? So the capital letter means that you need the full history for that page. Okay. So if intuitively, it only matters for Bob how many times he played one of the 2 moves, you think that the influence that he has in the game should be less than the influence that Alice has in the game. So, and this is what we actually show. So this we have these inequalities here that are very interesting, and these inequalities are for any P and any N, and this say that the probability in this game, where you need the full history, is bigger than this probability. So this probability where Bob has less influence in the game is less than the probability where Bob has more influence on the game. So this is very intuitive. And then here, so if you give to Alice less influence in the game, so this probability is bigger, okay, than this probability, because remember that this is the probability that Bob has a winning strategy. Okay. So we showed these inequalities here. So okay, I won't give you details, but what we use were Boolean functions, and we show an inequality using increasing Boolean functions. Okay, and for these other games, these are our conjectures. So, but we couldn't show that. So now actually we start to believe that are true, but okay, these are the conjectures so far. Okay, so we also show.
Can you go back?
Yes, sure. Ah, it's not possible to go back. Sorry, no, I think it's not. Let me see.
Escape the full.
Oh yeah, okay.
Yeah. No, I'm just at the asymmetry. It's because it's blocked that yeah, because I mean the first one you have capital A is less and capital B is more.
Yeah.
It's because it's centered above and this.
Exactly. And this one, I'm still assuming that this is the probabilities for both has a winning strategy, but now for us it's not so clear now that actually this conjecture is true. No. But yeah, I'm assuming that all these both has a winning strategy.
Yeah.
Yes. Oh.
It's random.
Yeah, it's super random. It's a random game. Okay, so we also show phase transition. So that means that there exist these values that are no 0 and no 1. And then when n goes to infinity, so this probability, if you take p less than pc, so again, Alice is going to have a winning strategy with high probability with the number of moves increase. And if you take p bigger than this pc, so then you are going to have a winning strategy for both with high probability. Okay, and so we also show a similar result for the other case. No, now in this case, Alice has less influence in the game. Okay, so you can see that something is missing. And what is missing is what happened at PC. Okay. And okay, we only show this actually that for this game, this probability doesn't go to 0 for this one here, and for this this probability doesn't go to 1. Okay, but then for this one here, this probability can go to 1 or can stay in an intermediate value. So the question is, can we say something else? Oh, this critical value, because this is the interesting value, right? So we run some simulations. And so you can see here the simulations. So then every cube corresponds to every value of p. Okay, and then here n is the number of moves. And this is the probability of having a winning strategy. And then you can see that below this value, right? Then, okay, they start to increase and then decrease, right? And then above this red curve, so everything goes to 1. Okay, but then the red curve is not so clear. Right? So you can think that, okay, maybe it goes to 1, but also maybe it goes to 0 or maybe it stay there. So, yeah, so this simulation suggests that the critical value is around this value here, and we start to believe that actually this goes to 1. We were super disappointed because what we want is to find again, right, where you have this intermediate phase transition, but it seems now that this is not the case, unfortunately. Okay, so we also show these non-trivial bounds for these values. So this value is between these two bounds here, and for this one is between these two. So one of these is not difficult to see because we already have this comparison with the winning probabilities. So you can use that result, and that result implies that actually this critical value of this gain is less than this critical value, and then you get this bound. Okay, the other two are not trivial to found, and then you need to use something that is called Thom contours. And these are some techniques that are used in percolation theory and also in mechanical statistics, but I won't give you details about that. Okay, and for the other game, for this game, no, and remember that this game is all that matters for the outcome is how many times each of the players play one of the two possible moves. So our results are a little less complete, and we could only show that if P is less than this value, then this probability goes to 0, and if P is bigger than this value, this probability goes to 1. So in this case, we couldn't show a Chart transition. Okay, okay, now I wanted to tell you some ideas, a few words of how we show this Chart transition. Okay. So for showing this Chart transition, we use something or some ideas from the theory of noisy sensitivity. So this theory of noisy sensitivity means that you have a system or a function, and then you change a little bit the input, and then the question is how much the output of that function change. Okay. Okay. What is the idea here? So I'm going to let me denote by G to N the gain graph. So think in this gain graph. Okay. I'm going to call. So I'm going to focus in this day. And okay. So then first, in order to use this theory, I need to define a Boolean function. Okay. So what is my Boolean function? This is the 0, 1 to this border of the gain. So this vertex is here, okay? And it's going to give me a 0 or a 1. So I'm going to assign, so what is the input of the Boolean function is these zeros and ones that I assign to the ellipse randomly, no, according to some intensity P. So the probability of writing a 1 here is P. And the probability of a 0 is 1 minus P. And then this Boolean function is going to give me what is the value of the root. Okay. If it's a 0, it's a 1, and then that means that it's going to give me the winning of the game. So it is not difficult to see, but we can show that the probability that this Boolean function is equal to 1 is actually the probability that both has a winning strategy. Because if this Boolean function has a 1, means that the root is 1. Okay, this is my Boolean function. Okay, so now what I'm going to do, I'm going to define what is pivotal. Okay. So for each vertex or each leaf, sorry, I'm going to define these two variables here. So these two variables are the same as the original assignment, except in the vertex B. So in the vertex B, one of the variables is going to have the value of 0, and the other is going to have the value of 1. And I'm going to say that this vertex is a pivotal for the Boolean function if they take different values. Okay. So in other words, if I flip one of the values in the list, if that change who is the winner, so I'm going to say that that value is essential for the outcome, and I'm going to say that that value is a pivotal, okay, for that assignment. And I'm going to call the influence of B is just the probability that this leaf is a pivotal, okay? Okay, so then, so we can show that this function is monotone, and we use this formula, this Russo's formula. And this Russo's formula says that the derivative, that the probability that Bob has a winning strategy with respect to P, so is the sum of all the influences, all the leaps. No, this is a very nice formula, because you have here a probabilistic point of view, and here you have like a combinatory, no, because you need to know, you need to sum overall the leaps, the influences of the peoples. Okay. Okay, so now what I'm going to do is I'm going to find a lower bound for that sum. So for that we use this inequality here that was shown by these authors, and they show that the sum of all the influences is bigger than C. This is a universal constant times the variance of the Boolean function times log of 1 over the maximum, right? So how can I see this formula? So you can think that if all the influences are small, so this maximum is small, then the sum is going to be big, okay? Because then you have here 1 over the maximum. Okay. Okay, okay, so then I'm going to use this to find a lower bound of the derivative with respect to P. And I'm going to use that this L is a Boolean function, so I can compute the variance. It's actually this Pn minus 1 minus Pn. And then if I assume that Pn is bounded away from 0 and bounded away from 1, that means that it's between epsilon and 1 minus epsilon, so I can bound this sum, no, using this inequality here, and it's bounded by this quantity. So then I need to control this maximum here, that is the maximum of all the influences. And then using symmetry, the symmetry that I have for the gain of Alice, that is the 3, so I can bound this sum by this to the power n times the supreme. Okay, so combining all these previous observations, what I can show is that the derivative with respect to P of the probability that Bob has a winning strategy is bounded from below by this quantity. Okay, so that means that P is increasing and P is changing, so the derivative of P is changing from a value, P is changing from a value below epsilon to a value above 1 minus epsilon in a window that is very small, and that this window goes to 0 when n goes to 0. So that means that I have something like this, okay? So I start here in a value very close to 0, and then suddenly I go to a value very close to 1, no, in a window that is very small. That is enough to show charge transition. Okay, okay. Forget now all that detail, so I'm going to speak about the other part of this work. Okay, so there is another motivation, and actually this was the motivation that we initially considered. And we wanted to find a model, a spatial model with an intermediate invariant low. Okay. And then, so usually in probabilistic models, you have two lows. One is the lower low and the other is the upper low. But it's not easy to find a models that have an intermediate invariant low. And this was our motivation. We wanted to find a model, a spatially dependent model, with an intermediate invariant low. So then the question was, can we find this kind of model? So why these intermediate invariant lows are interesting? Because that means that if you have these special models that interact locally, so if you start with this interaction, then you create something that is not real, something that doesn't go to 1 or doesn't go to 0, or more precisely, doesn't go to a lower bound and upper bound. So the question was, we start with a cellular automaton. Can we define a cellular automaton? So why? Because then we have precise local interactions, and can we find a cellular automaton with this phenomenon, with an intermediate invariant low? Okay, so then let me find the cellular automaton that we studied. So I'm going to start, so this cellular automaton is defining n squared, okay? And I'm going to start the cellular automaton again with the random variables, zeros and ones. Now I have all these zeros and ones in n squared, and according to this intensity p. So I'm going to put a 1 with probability p and a 0 with probability 1 minus p in n squared. This is my initial configuration. Okay, I'm going to define these groups. I'm going to call xn AB. Okay, this cellular automaton is going to evolve in deterministic integer times, and you are going to see why I'm calling AB. Okay, because it has a relation with the game that I just introduced. Okay, how are the rules? So depending on n, if n is even or odd, so I'm going to define this group. So I'm going to take in the coordinate aj, I'm going to take, if n is even, I'm going to take the maximum of these two coordinates, a to j plus 1. And if n is odd, I'm going to take the minimum of to ij and to I plus 1j. Okay, so those are my rules. And I'm going also to introduce this order. Okay, capital A and small b. And this is in the next time, okay, in time n plus 1, the value of the coordinate aj is going to be the maximum of aj and aj plus 1 if n is even. And in odd times, I'm going to take the minimum of 2j, j, and 2j plus 1, j. Okay, that are the rules. Okay, let me show you a picture because maybe it's not easy to visualize. So these are the rules for this cellular automaton. So what I'm doing, so I'm here, let's say that this is aj. So I'm taking the maximum here of these two values, and then in the other times, I'm taking the minimum of these two values. Yes. Okay, and for the other gain, so I'm taking the maximum of these two and then the minimum of these two, right? So you can see here that I have a dependence because it's depending on the value of that vertex. That are the rules. Okay, so, and this is my claim. So my claim is that actually the probability that Bob has a winning strategy in the games that we just saw is the same as the probability that this cellular automaton in the origin has the value of 1. Okay, and the same for this game. So the probability, this is the game that we introduced, and this is the game that PERT introduced. This is in the binary tree, and this is in this sort of product between the binary and the integer lattice. So this probability of having a winning strategy corresponds to the probability that the cellular automaton take a value of 1 at the origin. Okay. Okay, so okay, I won't give you all the proof, but let me try to give you some intuition why this is true. Let me show you for this game. No, this is the game. So this cellular automaton, and let's see why this corresponds to the game that I introduced. So in this picture on the left, so let's think that you consider. So here is one of the coordinates, and here is time. Sorry, time and one of the coordinates. And let's take a point, a t, okay? And this point, a t, here, let's say, is connected with 2i, but t minus 1, and 2i plus 1, t minus 1, okay? So what you can see here is that there are no overlap, no? And then you can see the tree, okay? You can see a tree here. And on the right, so if you consider AT, right? So then this is connected with AT minus 1 and A plus 1 T minus 1. Okay, and what we see here is the lattice. Okay, and then if you put this lattice tree, what you see is the gain graph of the gain that I introduced. Okay, so this is the reason why. Okay, what these probabilities are the same, right? Because this value, so the value at the origin depends of this value exactly in the same way as the root depends of the leaps in the gain graph. Okay, so then this gain here, so as I already told you, is related with this gain, the gain that PERT introduced. So for this, due to the tree structure, you have that these variables are IID for any n, okay? So this is propagation of chaos, sometimes it's called in midfield. And the product measured with intensity 0 and 1 are invariant lows. So that means that you start there, you keep there forever. And it has an intermediate invariant low, no? That is was PERT show. Okay. Okay. So, but what happened with our cellular automaton? Okay. What happened? Does there exist an intermediate invariant low? Okay. So, since we couldn't show theoretically, so we did some simulation. So let's see. So this is a simulation. This is time 0. Okay. And black is 1s and white is 0. Okay. Let's see. So this is time 1. So it seems that the number of blacks decrease, right? Okay, it's not so clear, right? Time 2, this is time 2. Okay, this is time 3. Okay, it seems that it's going to go to one of the trivial lows, right? Okay, N7. Right. Okay, N9. It's like, yeah. Okay, we can bet that it's going to go to all blacks, but oh, no. Okay, and this is N28. So you can see again here that there are a lot of whites. Okay, so then, so this is similar to this simulation, right? So in these simulations, the number of zeros decreases initially, and then start to increase again. Okay. So, okay, so then for this cellular automaton that is related to this game, so for this case, you have only independence in one of the directions. In the J direction, you actually lost independence. So we showed that the product measured with these intensities are invariant lows. But yes, but what happened with the intermediate invariant? So it's not so clear, but it seems that there are no intermediate invariant low. Okay, so let me finish with these questions for this other game. So this is the game small a, small b. So these are open questions. So does the game exhibit a Char phase transition? This is the first question that we need to try to show if we want to see if there is an intermediate invariant low. So does this game admit an intermediate invariant low? So does the symmetry of this game favor the existence of an intermediate invariant low? So these are open questions. So we don't know. So we think that maybe because in the game that Per introduced, there are a lot of symmetry. So the two players play in the binary tree. And in the games that we study, one is playing in the tree and the other is playing the lattice. So we don't know if losing that independence doesn't help to the existence of intermediate invariant low. So the question is, okay, so maybe in this game we can show that there exists an intermediate invariant. Okay, so the last slide is thank you very much.
We do have time for questions, so please go ahead. Don't be shy.
I have a question. It's not a good question, but it's a question anyway. It's about the constant. You have an inequality where there is a log, and you've mentioned that there exists a constant there.
Yeah.
Is there's a way to know this a sharp constant? What should it be?
Oh, okay. Yes, I don't know if it's sharp. I know that it's a universal constant, but I don't know if yeah. I don't know if it's sharp. Yeah.
I'm interested in sharp constants. Sorry.
Yes, yeah. Not sure. Yeah.
Thank you.
But that inequality is very interesting because actually it's not very intuitive because it says that if each of the influences is small, the sum of the influences is big.
Thank you.
Any other questions or comments?
This is a vague question because I think you said something about the motivation of switching from the three games to these games where you have lattice and tree, the product of lattice and tree and so on. Can you say a little bit more in statistics or in probability, what kind of problems lead to such situations where you want to model the games that are not tree, but that have this sort of, can you give more examples? The reason I ask this question is that we are extremely used to binary tree games, but some other people here work in model theory. We're full of those games, but they're all tree games. Very good, sometimes infinite trees and so on, but tree. And this kind of blend of trees and lattice, sometimes kind of I have the sort of idea that I've never come across this sort of thing in that area. So what kind of problems?
Okay, yes, okay. So our real point was actually something very different to this. So we start trying to find an interacting particle system with an intermediate invariant low. This was how we start. And then we end up with this cellular automaton, right? And then at the very end, we realized that this cellular automaton has an interpretation as a game, right? Okay, and then so when we were reading in the literature, we found that this kind of games could be interesting, but more in computer science. because so for these search algorithms, right?
Yeah.
Yes, but so from the point of view of computer science, maybe this is the motivation, and for us was more from models that are especially dependent, and we wanted to find intermediate laws. Yes, but yeah.
But these concepts you get in the intermediate laws, as Professor Oscar Riaño was saying, they seem to have a lot of meaning.
Yeah.
Like when it is not 0, 1, but go 2. So that constant, that's a very strange phenomenon that seems to, I don't know.
Yeah, it's a very interesting phenomenon, and we wanted to find more and understand more this kind of intermediate phase, right? But yeah, and this modification was like, okay, let's do a small modification and let's see how far we can go.
Nico?
Thanks, Natalie. Yeah, beautiful talk. I want to know if you can extend those games to the context to evolutionary game theory. And if you could that, could you extend or expect something like this dot behavior?
Okay, so there are one word in the question that I don't evolutionary game.
Evolutionary game theory.
Yes, I don't
It's
know
like
what is that.
it's something like IDO that the game learns about the last step, something like that. Something like the game itself can learn about the previous one.
Okay, yes, sorry, yes, I don't know. So, okay, maybe we can. Yes, I don't know. So, because as I said, so the motivation started in probability, right? And then we end up with this game that has this interpretation, and we were looking a little bit the literature in computer science, but yes.
One last question to Bella. Go.
I want to ask you 2 questions. First, about generalization of this idea. What about if we have 3 players, or n players, or a left player?
Okay, a left player sounds difficult. But if you have n players, yeah, you can extend it. Yeah, this, yes, I think you can extend these results. But yeah, left player, yeah,
And the second question is the structure of the tree of the tree you presented. Remembers me a lot about model theory, in the sense of we have a formula and we have 2 possibilities of 2 values. So what are the relations and the interpretations we may have about these 3 and model theory in logic?
So okay, let me see if I understand this. So what is the interpretation of this game with real games?
No,
No.
Model theory in logic.
Okay. Maybe Andres can yeah, sorry.
We can talk about that as well. People here.
Okay, I think we can then finish and thank Natalia again.
Yeah, Tomar valores muy centralizados. That's really
Ahora mismo está por aquí. Ahí no sé, bueno. Claro, pero no sé cómo el comportamiento, la persona estaba ahí.
Yeah, if they have the strength more like agave. Yeah. Exactly. So that's good. Yeah, we're going for. It should be okay. And we're always fine.
Los viernes siempre
Yeah, I saw.
No hemos podido. Eso está haciendo muchos años. La parte de los otros está dentro de la porque esas dos. Pero ya no.
En que muchas personas están conversando. En que vamos a se llama Randuca y la gráfica no también se Exacto.
Excelente exposición.
Sí, gracias. Me tomé una galleta. No, porque yo siempre espero que los estudiantes.
tiene que hacer para el almuerzo hoy?
Exacto, sí,
Estás indicando En las siguientes cuerdas, ahora entonces, todo eso viene de la situación pero la geometría es Pues básicamente es parte de un recurso de esta celebración de la elección. Eso también tiene importancia. Luego esta parece que solo carácter. Básicamente lo mismo. Esto no parece. Si todo esto aparece en la voy a pedir que hagan eso. Y si me dicen que no, entonces cuando tenemos este no, que la pusieron. Cantidades espaciales. Sí. Sí, pero que la esto es
Oscar mandó la presentación.
Sí, y
Y está grabado. Pero no se oye, si no pones esto no se oye.
No, aunque me digo que no hace falta. Ah, sí.
Pero para los videos no por ahí. Pero lo que tienes que hacer es apagar el micrófono. Yo prefiero empezar eso.
Para esto es más fácil. Todo es un problema. Ya para que lo apoyo. Pero ahora mandamos.
Ah, sí, 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 sí. Sí, exacto.
No creías que lo ibas a lograr.
Es que ustedes no saben.
Ah, muy bien, sí.
No es así.
Buenas noches. Y el lunes.
La presentación de esta tarde está Ah, qué chévere. ¿Así? ¿Quieres? Ah, qué bueno. Aunque sea así.
Okay, I think we can go ahead and continue. Then this is the second morning talk. Then it's again my pleasure to introduce Professor Oscar Reaño. He has a PhD from, you have a master from here, right? Master from here, from our university, and undergrad. Also from here. So it's almost local. And then he has a PhD from IMPA, Instituto de Matemática Pura y Aplicada in Rio de Janeiro, under Felipe Linares' advice. Then he has been visiting around. In particular, he has a postdoc position at the Florida International University under Svetlana Rudenko. And he is interested in PDEs, especially in specific PDEs and other interests. And he's gonna talk to us today about an introduction to dispersion, nonlinearity, and solitons. Oscar, thank you very much for accepting the invitation to come here and talk us about your research. The floor is yours.
Thank you. First of all, I would like to thank the organizers for the invitation and of course for the great opportunity to give this talk today. So this is, honestly, it's an introduction. So it's very not something rigorous, it's just an idea or something to introduce you the notion of a dispersive idiot. That's the idea, okay? That being said, this is the outline of my presentation. I'm gonna focus on some preliminary things on dispersion, nonlinearity. I will try to explain, maybe I will do an exam at the end. No, sorry. It's false. It was a joke, by the way. Anyway, I'm gonna tell you more or less my intuition about what is dispersion and what is nonlinearity, okay? And then I'm gonna show you something about nonlinear dispersive equation, and if time allows it, I will show you things we do very, very, very at the end in the department, like the group we have. Wow, so something happened. Okay, so this is the question we're gonna address today, is what will expect a way, or what would you expect a way to do? This is the big question I will try to address today. And the idea is that if you have a way, look at the picture there. If you have a way, you start to realize that the wave should spread out, should start to decrease and disappear, right? That's that's the general intuition, right? But there's something, sometimes a wave can travel a very long distance without changing its shape. So you will find a special wave that never changes its shape. It's always the same. This is very interesting. And it's actually contradicting our intuition. So I will show you models that justify why this is happening or why this is possible, okay? Anyway, what's happening? Okay, anyway, so let's start with an observation from the 1924 for the Scottish engineer John Scott Russell. He observed like something, a new wave when he was like close to a canal, and he observed the following phenomena. I think I can describe it better with a picture here. There was a boat, and the boat suddenly stopped. When the boat stopped, then it creates a wave that started to move in the shape they are observing right now. And he said like, oh, that wave looks interesting, right? So he started to follow the wave with his horse, like the best horse he has at that moment. And he followed the horse, and there was something really interesting. It seems that the wave preserved the shape and the speed. So it looks the wave all the same. It was not decreasing. Like amazing, like preserving the shape. Really nice, right? And that's a wave worth chasing. Anyway, the idea, the context of that canal was in Edinburgh in the Union Canal. And why the wave was generated, I will try to explain later. But the idea essentially is because we are in something called the shallow water regime, that the water is not so deep. So because of that, the wave or the original wave appears in that moment. So I have some pictures here which make the phenomenon really interesting. It appears, right? And because of that, Russell started to do experiments in his garden. Of course, he has a very big garden compared to mine, anyway. And doing that, he's starting to do that. But there's a reason why he got interested in these things, because he was designing boats. So he wanted to make a very nice boat. So he was thinking like, okay, maybe I can incorporate those ideas. And actually, he reported the idea in this paper, some report of waves, present to the British Association for Advanced, and there's the dates. I'm not gonna read. Anyway, so this is something really nice because that was the first observation, or at least, I mean, it appeared before, but it was the first like rigorous report of wave, and it was later something that we will call solitary wave. Solitary because it's like not changing the shape. Anyway, so that's the idea essentially. Let me probably move. And this is like what Russell he did in his with his experiments, and the idea is more or less what you're observing right now. He has like there's water here, shallow, not so deep, okay, and he dropped a wave on one side. Depending on the wave, it generates this kind of nice wave, and thanks to that wave, he started to observe how it moves, how it travels. So during his experiments, he found like some relation between the wave and the amplitude of the wave, and of course the speed as well. So it was like what he was doing. He liked to play with things, right? Playing to create waves. Really interesting. Anyway, and so here's the idea, or things that I want to mention. This moved really fast. Yeah, it's not this thing. I'm sorry, have to go back a little bit. A lot.
It's some delay, so you have to push, you have to wait a little bit.
Ah, that's the, sorry. I got it now. Thank you. So anyway, so here's the idea. The idea is now the question, why that wave exists? How is it possible, right? That's the question that I'm trying to at least give you an intuition what is happening today. And that is the thing we want to solve today, at least for the very not mathematical point of view. And so I will start addressing the question of what is dispersion. So I'll try to explain two things that create the wave, dispersion and nonlinearity. When they both combine, it generates the phenomenon called the solitary wave. Okay, and here you can see a picture for the 95. And in this picture, they try to create Russell experiment. They jump on this kind of boats, I don't know, and they try to generate the wave. I don't know if you can see it correctly. It depends on the resolution, but I think it's kind of clear the way they try to create. So it's shallow water wave and some wave on one side, generating the wave that you're observing right now. So it's a nice picture. So we can try that experiment. Now that we have something here in the university. But anyway, so let me talk about dispersion. Now we know the phenomena somehow, the wave that exists, and I'll try to divide it in two parts that create the wave. The first part is something called the dispersion, right? So to study the dispersion, we study something called the frequencies. That's the best way to understand what's happening. So you start with a wave, think about this thing here, the blue one, a wave there localized. And the idea is that using Fourier transform or studying the spectrum, the composition, if you understand, think about writing the wave as sum of sine and cosines, right? As Fourier decomposition of the function. Anyway, because of that, we can pass the function, the problem to understand the frequencies, right? And I mentioned this here. Like using the Fourier transform, we can understand the wave in a different space, a space of frequency, when essentially we're studying the spectrum according to this base, which is not always a base, but let's talk that is the exponential base. This kind of understanding the frequencies, right? Even when we talk, there's frequency decomposition in our voice, right? So that's essentially the idea here, using Fourier transform to understand what is dispersion. So let me move next. So there's also another thing that I have to mention is what is a linear evolution PDE. The word evolution means that you have a free variable, which we will call time. So it's an equation, a partial differential equation that has some free variable or a different variable, which we're gonna regard as the time evolution, the time variable, which describes that a process is moving in time, right? That is a linear evolution PDE. And I had mentioned some examples here, like for example, the heat equation that probably we are familiar with, the free Schrodinger equation also appears in quantum mechanics. And here's the area equation as well, which will be important in our talk in a few slides. Anyway, so this is essentially what is a linear PDE. For now on, I will work only on linear PDEs. Anyway, so now we want to find a very, okay, probably. Sorry. Things faster. Yeah, it's comfortable this way. So now we want to find something interesting and to understand what is the dispersion. To understand it, we're gonna look for very particular solutions, are those exponential solutions. They sometimes call the plane wave. So connecting what I said before, we wanna understand the frequencies or the composition in Fourier of a wave. So how to display the solution. And one way to do this is to study just one particular frequency. And that is the one given by this exponential, right? So I take one particular solution of this form, and I want to plug it into the equation, and then I will find this thing here that is called dispersive relation, this omega that appears here, right? So it's the dispersive relation that appears there. So what we're doing is we have a PDE, and we insert this solution to check if the equation is dispersive or not. That's the thing. And we're gonna say formally, because it's not rigorous, we're gonna say that an evolution equation is dispersive if the dispersive relation is a real value function, first thing. And the second thing is like this quotient here tends to infinity when the frequencies goes to infinity. This thing here is called the velocity of the wave. You can find it by taking the phase function, but probably it's too technical to say, but you can find it by taking, wow, by taking this particular solution here and you want to check the speed of this thing here. Just so you differentiate that you will get the speed of the wave, which is essentially what is happening here. And approach it. This is strange because I push forward and it goes backwards. And I push backwards and it moves forward. This is really random. It's really a probability of. Yeah, it's kind of crazy. Okay, anyway. So it doesn't matter. So what's happening essentially, sorry, I want to mention it, but anyway. I spoiled you, like say that. Okay, what is happening here is essentially because of this thing is increasing and going to infinity, the speed is changing. That means that different frequencies move at different speed. So the frequency is not constant. Like that is what it means to be a dispersive equation. That the frequencies are moving at different speed. And of course, no one will understand that, but I will show you a picture in a second. Yes, this is moving forward again. And there are some examples, like the heat equation is not dispersive because this function, if you plug this solution into the equation, and then you will find that this thing is not real bad. So essentially what it's saying is you have exponential decay because it's the heat equation. There's also the Schrodinger equation, which is an example of a dispersive PDE. The equation is also dispersive PDE. And a more sophisticated, a complicated example is this one called the Benjamin-Ono equation, which you can find, plugging this solution will give you nothing, because there's this operator called the Hilbert transform, which is a non-local operator, which what it means to be local is kind of like a derivative, which to compute it, you need to compute a whole integral on the R. It's actually a principal value. But anyway, this is an operator that appears. So these are examples of dispersive PDEs. And so because honestly, it's not that easy to understand, what I'm trying to say is the following. What the dispersion is doing to your wave. So what it's doing is like, since different frequencies travel at different speeds, they are separated, the localization is lost. What it means, you start with a really localized data. A dispersion, what it's doing is spreading the solution. It's not disappearing, so don't confuse with dissipation effects. This is just spreading the solution, spreading out the solution. And with the next slide, I think I'll try to explain it better. And this is the next slide. So what it's doing is the following. Imagine this as a wave package. So a wave package is the whole wave outside. Inside that wave, the wave is composed by a sum of different frequencies of different waves, like the blue one you're seeing right now. Okay? What dispersion does, I will focus on the blue one, is that according to the time evolving, the original frequency starts to increase, the speed is changing. As you're seeing right now, the frequencies is starting to oscillate. The frequency disperse. This is dispersion. And what is happening, and this is also important, is that the mass, the total thing there is not disappearing, it's turning into more oscillations. So it's not a dissipative. It's not like the wave is decreasing and getting smaller. No, it's like the frequencies are turning into more oscillation. This is dispersion. Dispersion is when you have more oscillation. I probably should start with this. This is easier to understand than the frequency relation and those things. But anyway, so this is essentially dispersion. And a word that I like is like localization is lost. So again, this is a very localized data. And after dispersing, you see the frequencies, it starts to disperse. And you observe this. We are all familiar. We went to a pool, right? In the beach. You see the waves moving like this, right? So that is dispersion. So this is pretty much my idea. Sorry if I'm not being rigorous, but I just want to give you an intuition what it is. Okay, and now it's not good. Anyway, so because of that, okay, that's dispersion. So keep in mind, okay, this guy is talking about dispersion. First thing to notice, so dispersion. And the second one that I want to call is nonlinearity, nonlinear effects. So the nonlinear effects, to understand when something is nonlinear, we always talk that it's what it means to be linear. So to be a linear equation is that you have two solutions, and the sum of the solutions, even linear combination of this solution, is still a solution. So that it means for a PDE to be linear, right? And nonlinear equations are equations that do not have this nice property of combining or superposition principle. And the idea of this, the typical example that we study is the nonlinearity. This guy that you observe here is a classical example, the Burger equation. in biscuit because you don't consider the viscosity there. And what you're seeing right now is this nice equation, U times U, derivative of using the x variable. So this guy in total is something called the nonlinear term, the Burgers equation, okay? So this is nonlinear because U is coupled with its derivative, with the slope, with the speed somehow, right? Because of this guy here. U times Ux, that is the nonlinear term. So this is a particular example of nonlinear term. So what's happened? Typically you study when you take a PDE class, first PDE class you take as a grad student, you take the Burgers equation and you find that there's one technique to solve it, that is the method of characteristics. And the method of characteristics shows you that there's an explicit solution of that thing, which is really strange because the solution depends on the solution itself. U is equal to f of x minus u. So it's an explicit formula. You can even solve this equation using implicit function theory as an application. Okay, and what it's telling is you can show something really interesting in this type of nonlinearities, and is that along there's something called characteristic lines, which I'm not gonna focus on that much, but the function is constant of characteristics lines. What I'm trying to tell you with this thing is that something is gonna happen, and it's the following. If the function is constant in these characteristics lines, there might be a point when the slopes of the constant, the slopes of these characteristics lines intersects with the other. When that happens, that is something called a choke formation. So it means that because of the nonlinearity, you expect a phenomenon called chokes. It might happen, but careful, this depends on the initial data you use. Like for example, if the initial data is decreasing, you can find a time when this collects, when this explodes, like something some people call time of blowout. So because of the equation is explicit, you can find a point where it will generate chokes. And at this point, some of you might be saying, like, I don't understand what this guy is trying to say, which is correct. So I put a picture, which will explain better. When you have a nonlinear function, is when you see on the beach, the wave starts to collapse. So the wave starts to be more pointy, I don't know, to be more, like it starts to collapse. I don't know, you all have been in the beach or seen a wave. The wave is tied to something that wave steppens and wave breaking. The wave breaking is like when the waves start to collapse, when it starts to get together and it starts to lose its shape, of course, and it starts to turn into this thing that we are seeing at the very end of the figure. That is happening because of the characteristics. It's saying in terms of physical terms that one wave moving, like, I don't know, like the very top is moving slower than the bottom. So it tries to collapse. So there's a difference between the two speeds there. And that is what is happening with the nonlinearity. The nonlinearity introduced this type of phenomena there. Right? It's easier to understand with the figure again. Right, so we all been in the beach or seen a wave collapse. And so where's the magic? Dispersion generates a spread out, loss of localization. And nonlinearity is causing something that is called breaks. This also has a different name, I forgot to mention. It's something called wave breaking. That name makes more sense, right? Because it's a wave break. So wave breaking makes clearly more sense. So a combination between wave breaking and dispersion, when they're alone, they're trouble, right? They're difficulties. They're not helping you at all. But think about the balance. What is the balance that creates these special kind of waves that Russell observed? And the balance is that dispersion is trying to spread out information, while nonlinearity is trying to create breaks, to combine, to join everything. So when you have both of them together, an equation with dispersion and nonlinearity, they are fighting, competing each other. And at the end, you will see that the balance, the existence of those waves is because nonlinearity and dispersive effect compensate each other and create the magic. So the magic appears because of those two effects together. I hope I made that clear. Anyway, I put it like this. Together they can cancel. Dispersive prevents breaking. Nonlinearity prevents spread. So that's like both phenomena are bad behaviors, but together they turn into a good behavior. Really strange, right? But in physics, it works like that. Real world happens, right? Anyway, so I just want to mention this is the typical equation, the model that justified when you can get exactly a Russell solitary wave or the not changing the shape wave. And this is the equation we have. It's an evolution equation, and you have two terms together. This term here is nonlinearity. We already observed this is the nonlinear term that comes from the Burgess equation. And this guy here is the dispersion term. So I put here all the things I explained before, like dispersion, what it's doing, and nonlinearity, what it's doing separately, but together they have a balance. That's pretty much the idea. And this is the example that is there, a typical example there. And let me maybe move forward. Perfect. Perfect. I don't think so. And this is the exact. So the Russell solitary wave, the wave that he observed is exactly this sesh, the hyperbolic sesh of this function. What he observed was this function. So this is a solution of that dispersive equation. So this is a particular solution, and this is the wave he observed, mathematically correct. So the KDB equation, the model I showed you, is really interesting because it has this particular kind of solution. And I put in this plot, there's some graph. I changed the parameter K and different values of it, and depending on it, of those things, I construct different waves. That's pretty much the idea. And this is nice because the equation turns out to be a nice model when dispersion and nonlinearity combine together. And when you have them together, you can find this explicit super nice function. And I love this sesh, the hyperbolic sesh, because sometimes when you explain this equation, the hyperbolic function to your students, you say like, okay, where can I find a hyperbolic sesh, right? Like, is that even useful? And yes, it is. And they're solitary waves. And they have exponential decay, of course, because of the hyperbolic sesh, right? Anyway, so I want to show you. And these things look like those waves, right? Really nice waves there. Anyway, so summarizing things, you can try to have an equation and see if that thing has solitary waves or have waves that do not change its shape. And this is something called traveling wave. What is a traveling wave? The name said it all. It's a function that it remains the same through the dynamics of the solution of the equation. So it's a solution of this form. You have a function f applied to x minus ct, and if you observe as time moves, the equation has a shift. So it's moving with c times. And this is something that it's called a traveling wave solution. And in general, I just did this graph here to show you. Really what is the idea behind a traveling wave. Oh my gosh. Okay. And so finally, I can define one of the things I mentioned in the title of the talk. What is a localized traveling wave? A localized traveling wave is a traveling wave that we also ask to decay as c goes to infinity. This is a different variable, right? As the function is decaying, it's vanishing at infinity, like the wave, right? Like that wave is vanishing at infinity. And this is called traveling wave. People call it solitary wave. So this is a solitary wave if satisfied these two conditions as well, right? And there comes a different word that sometimes is mixed or get confused. For example, when I talk, I always mix these two terms, traveling wave or solitary wave. But in this talk, they're the same. So I'm saying. And there's a different word that also I mentioned in this talk that is something called a soliton. Soliton sounds like a particle, right? Like a soliton, like something that is a particle. And that is essentially the idea here. A soliton is a very special type of solitary wave with an additional remarkable property. What is the property? If you have two different solitons with two different speeds, with mean different heights, or same time, when they collide, when they merge together, after a certain time, they're separate as nothing happened. And when that happens, those solitary waves receive the name of solitons because it means that they behave as a particle. And you don't have to believe me. I will show you a video in a second. Right? So this is really the difference, and I want to emphasize that. And this is really nice because Russell observed in this year what it was a solitary wave, so a wave that is not changing its shape, that it was really nice. He followed it with his horse. But then 100 years later, the word soliton came to life. So this is really interesting because it's something that we observe, and then we need centuries to develop a theory to understand what we saw. That is essentially the history, the whole picture there. And so the localized, there's collisions. So let me show you videos of these things, because I don't want, probably I'm talking too much. I still have time. Can talk more. See, there, so this is okay. I'll just watch, please. Shape is the same.
Real.
That's real. Yeah, that's a good. I don't pay. I don't have the money to do that, you know. Can you repeat it again? I just want to emphasize that. Okay. They're paying me for this. I receive money for this advertise. Wow. I just want to show you how they create. They let this wave fall. There's something falling that generates the wave. So this is Russell experiment. It's the same as Russell experiment. So you let the wave fall, and then that generates the wave, and the wave moves. Okay, podemos parar ahí si quieres conocer lo que. Always better to explain with videos.
Next, please.
Next video. Okay, here's the collision of solitons. Probably will take, it's probably what I said, like this is solitons because they're collide and they're separate. Okay, you stop. It's gonna be really fast, so I'm sorry. So there's the two solitary waves, they collide, and they separate. That is a soliton. Let's repeat it. Thank you. So that is in physics, that is called to be elastic collision because it collides and then they turn into a cell. Really nice. Actually, to prove that mathematically, it's super hard. Super hard. I think there's this school in France that they study how to prove those collisions. What happens after that? Thank you. Next. So that was the nice part of the talk. Now we come back to the slides. Okay, so remember, we have a model, right? We propose there's an equation that solves the thing. The equation is essentially describing the phenomena, really nice. And why this is possible somehow. Again, the balance between nonlinearity and dispersion. They are competing and helping somehow. And there's also because KDB is not just your regular equation, right? It's a super nice equation. It's an integrable system, infinitely many conservation laws, explicit multi-soliton solutions, remarkable collision properties, inverse scattering transform. So it has super nice things. KDB is the best equation that you can have. It has all those properties, right? And this, of course, opens more questions. If I have a different model for a different situation, does it satisfy these things? So that's the other point. Okay, this is comments, just what I was saying. Anyway, I just want to mention this, summarizing the history of the soliton work. And it started with, funny enough, it started with Russell observing the phenomenon. I think later Korteweg debris, because that's the KDB equation. Those, I don't remember. One of those were a PhD student and the other was the professor. So that was part of a PhD dissertation when they proposed the KDB equation. They say this is the KDB equation and this equation has solitons, has solitary waves. There's some gap here, which I forgot. And actually, Boussinesq, he was really good at that moment. He proposed the equation, and that equation that he has somehow was a good model to represent solitary waves. But it was in this work of Korteweg debris that they simplified that equation and arrived to a super simplified version of the equation that justified the existence of this kind of waves. Anyway, And this is just people that continue working on that. As you can see, there is a gap here. There was a lot of years that people were not interested in these equations, right? That's what I always mention. When you get 0 citations, you never know. Right? In 100 years, someone will cite your work. Right? Hopefully. Yeah, sometimes you do things and you don't know where it's going to be recognized. But what is important, and I want to point out, is that there's like the numerics help really to understand these things. There's like these guys, Fermi, Pasta, and Ulam, they try to understand the KDB using simulations, computer things, and checking what was happening. And because of them, the equation got like a super, how can I say, like promotion, like it was like, I don't know, like promote the equation a lot. So thanks to numerics. So I think that this is a nice story, right? You start with an observation, then someone proposed a model, and then using numerics, people start to understand that it was relevant. This is important. And KDB has application in a lot of things, even neural networks. When you think, maybe you have a solitary way sending some knowledge or something. So it's really interesting. Anyway. So let me tell what is a nonlinear dispersive equation, those are like things that I work a lot. I did my PhD on that, and my current research is on those type of equations. And that is essentially what I'm going to mention right now. So what is a nonlinear dispersive PDE? A nonlinear dispersive PDE is called dispersive if it's not linear and the linear part is dispersive. And that's it. And I like this picture as well, because see, we are seeing now the dispersion. This that you're seeing, that radiation at the end is dispersion. So it's not that the wave disappears. It's not that you have like the wave starts to disappear. That is a different phenomenon. It's just that the mass starts to turn into these oscillations. That is dispersion. And you see that picture there. Anyway. And what is interesting, I did a little small spoiler there, is like, of course, waves, they just don't belong to water waves, right? You can find waves in a lot of things, like sound waves, waves on a string, seismic waves, electromagnetic waves, quantum wave, internal waves in fluids. So waves appears in several contexts. So imagine in each of these contexts, you may find a different dispersive PDE, and then ask same questions. Do I have solitary waves? The collisions are elastic. Okay, so that's the point. And this is more or less the general formula of nonlinear dispersive PDE. You have the nonlinearity, and then you have an L of U, which is an operator, which is dispersive. In the sense, I define it a lot, like the dispersive relation divided by the frequency tends to infinity when the frequency goes to infinity. Anyway, so this is like different, I put water, strings, light bulbs, and you can find dispersive equations as well. Well, what do we study? Okay, we are also mathematicians, right? So we also want to do something with these things. We have a lot of things. So here are some typical questions that you may ask. And some of them, let me start. Well process. What is well process existence? Okay, if you have a model and there's not existence of solution, that is not a good model. So existence is like the first part. Here you may find questions as something called minimal regularity, like the worst solution you can put on that equation and still get solutions. Like think about when you're in a pool, you hit it with a fist, very strong. It creates a delta function, and then the solution is smooth and turns into a better thing. So that's the kind of question, well process. What's the worst initial condition you can have to have an existence of solution? There's this question of scattering. Probably I'm mispronouncing it. I always have problems pronouncing this word. And this is the large time behavior if your solution at the end starts to behave as the linear one, when the time is really large. Blow up, this is something that I talk with my colleagues. The blow up is if this is a good or not a good model, if at some time this starts to explode. Like you have a condition that explodes. So that is something called blow up. Stability and instability of solitary waves. Now you have these particular solutions called solitary waves. A nice question is, are they stable? If I make perturbations of them, eventually the perturbations of the solution remain the same. Is it stable under perturbation, or is it just separated? So just a little bit of spoiler, instability is always somehow connected with blow up. Anyway, and summarizing all of these things, long time behavior. when the time comes to infinity. I mean, if I have global solution, what happens when time goes to infinity? Can I describe the solutions? And more and more and more and more questions appear there. There's a lot of questions. I don't know, like recently, connected with the previous talk. Like there's always this equation and you add an stochastic term. When you add an stochastic term, you don't have conservation of energy. So if you don't have any conservation energy, do I have local well pulses? Do I have all of these things? So it's always nice. There's always questions with this. There's always things to. Anyway, so I just want to summarize some examples of nonlinear dispersive equations. This is the Korteweg-de-Vries equation, KdV. We already studied that equation, and I'm gonna change the name of the solitary wave by Q. Q. Now it's gonna be Q, and it's a translation of that. And Q is a profile there. There's a really, really interesting thing here, and it's proof uniqueness of solitary wave. Uniqueness, there's not possible to have uniqueness, but it's unique in a class of solution, positive and being even function. Because they're positive, right? They look like a wave, and they're even if you start at the origin, and then it travels, right? So there's uniqueness of this kind of solitary waves. Anyway, and so here comes the question. Okay, one single soliton was nice. Oscar showed us 2 videos showing us that thing matters. That is important, right? Having solitons is interesting. But what happens if you have a complicated initial data? If you start with something really chaotic, something that is not nice behaving, so that's essentially the question here. And the big conjecture we have in nonlinear dispersive equation is something called the soliton resolution, the big conjecture, the big monster here. This is the conjecture that appears in those dispersive PDEs. What it says, it's really nice. It says that if you have a dispersive equation that is global, eventually the solution will behave as a sum of solitons, a sum of solitary waves, plus radiation, and depending on the equation, coherent structures, and other things like research on different things there. But what is happening, and what I want to point out, what this is a big conjecture, is because the solitary waves are nice. Okay, they're nice, they look nice, but they also connect with the large time behavior of solution. That's the conjecture. So you can start with a very weird initial data, but eventually your solution will turn into a sum of solitons. So that is a big conjecture, right? And I just mentioned this paper of Terence Tao, why are solitons stables? And he explains way better than I say soliton resolution in general, right? So that's the soliton, the big resolution. So the solitary waves are not always nice, but they also connect with the large time behavior. And that it has to make sense to you guys, because even with the waves too strange at the beginning, at some point it starts to turn into nice oscillations. So it's really intuitive, right? At least. Right? How much time do I have left? Oh man, I still have half an hour.
No, 20 minutes.
20 minutes? Okay, talking too much. Anyway, so let me show you, this is the soliton resolution conjecture for the KdV. And this is what I was saying. It says that for very large time, the solution behaves, this behaves is like super, I mean, anyway, behaves as a sum of soliton plus radiation. Radiation is the other thing that you cannot describe what it is exactly. And this is the soliton resolution in the case of KdV. What I was saying in my previous slide is that depending on the equation, if the equation is different, you have to add more terms, breezers on another coherent structure there. So you put plus, breezers, plus another thing. Breezers are solutions that are periodic in time, that repeat in time. And this is the conjecture for KdV, right? Next slide. And this is what is known for that conjecture so far. For KdV, it's known, for the KdV equation is known using the method of inverse scattering transformation, right? It's also known for a different nonlinear version of the KdV, which is called the modified KdV, also using inverse scattering transformation, but still, we are mathematicians. We will, using the inverse scattering transformation is putting a lot of hypotheses. So the conjecture is still open for solution that does not satisfy the inverse scattering transform. So it's still open for KDV, right? For the nonlinear wave equation, which is also people consider as a kind of as a dispersive equation, there's a lot of super nice papers of Thomas. I don't know how to pronounce his name. He's French, and I'm sorry. Carlos Koenig, he's from Argentina, Mer for France, and several collaborators. They have like the resolution, the solitary resolution conjecture for the wave equation. They have in some cases. And very, very, very recently, the papers is still on archive. There's this group, Patrick Gerard, Gassot, I don't know what is the student, anyway, and Miller, Gerard, and Gassot, they together in 2026, there's a preparing on archive when they proved the solitary resolution conjecture for the Benjamin-Ono equation, but for some initial data. Actually, initial data has to be like in a short class or have super nice decay. So this is still an upper problem for arbitrary. And it was like a big, big, big thing there. And it appears this year. It's really nice. And again, let me show you a picture because probably I'm not explaining that good. As an example, I'm taking these two models. I work with these toy models. And what I did is like consider the Burgers equation, but still of that, notice that I put an alpha power there. You see? I put an alpha power here. I consider the same equation with the alpha power, but the absolute value. The idea is that what we do is like playing, like when you raise the volume of your car, right? So if you move the alpha, you are increasing the nonlinearity. And probably nonlinearity is beating up the dispersion. And if you lower the nonlinearity, oh, you have a question, sorry.
The conjecture states sufficiently general initial conditions it holds. Okay, not for all initial conditions, but sufficiently generic.
Like
at least in KDV, do we know for which initial conditions it's not true? Because maybe there's a measure zero very strange conditions where it fails, because that's what the conjecture says. It's not for everything, it's generic. Yeah, so maybe there's a bad set of conditions that people know, look, there is a problem. Do we know it in KDV at least, or we don't?
As the thing like those conditions you will rule out if you have global solutions. So conjecture remains each time you have an initial data, you have global solution. You can find a class, I mean, the conjecture for KDV, if you take H, a delta correlate H minus 11, for that you don't even have solutions. You don't expect to have solutions. But as long as you have, if it is global, the soliton should hold. That I should say. Of course, there's always like the smooth function that decay faster than any polynomial, the short class. You find that a soliton resolution holds. Thank you. Nice question. Anyway, so we have these two models here. Please raise the hand when I have 5 minutes, because I'll keep talking. And when I was preparing this slide, I made a mistake because this is the first one. Time equal to 0, and then for some reason I put different. I didn't notice. Anyway, sorry. So this is what I want to show you: the soliton resolution using numerics. By the way, completely open. Oh man, come on! Completely open for these two models because I changed the nonlinearity, and the equation doesn't have inverse scattering transform, so it's completely open. Anyway, so this is the first picture, the time equal to 0. If you notice, the initial data is a Gaussian. It's an exponential to the negative x square power. So you can notice that this is the time equal to 0. Notice that as the time evolves, the equation, let's check time 200. In time 200, the solution splits into a sum of solitons. This is a soliton, this is a soliton. These lumps are solitons. So I have to be careful to show you here. In blue, you will notice the solution of U. In dotted, in those dashed red, you will find the solution of B being, yeah, the probability of getting this correct is equal. Got it. So this is U without the absolute value, and this is B with the absolute value. Anyway, so I'm not caring about that much, but what I show you is that honestly, you start with a really nice localized initial data, and you start to turn into a decomposition of solitons. You see the solitons here. This is really nice. So this is the soliton conjecture using numerics. I think we did that with some collaborators. Anyway. There are other examples like the nonlinear Schrodinger equation with the focusing terms. This is different because it's complex value solution. We look for complex value solution of the equation, and this equation appears generally in nonlinear optics theories, laser, Bose's ice-stain condensates. Probably I mispronounced that, but I'm sorry. So this is another example of solitary waves of dispersive PDE, and this is the solitary wave defined there. This is slightly different. You want a solitary wave to be invariant under the rotation group, to be invariant under that rotation, and you will find that those equations has to satisfy this elliptic equation. And there exists, for some parameters, a unique solution. I'm just showing you now examples of these dispersive PDEs. There's the Hilbert transform, the Benjamin equation, the one I mentioned that in 2026 appears the solitary resolution. And then we have the non-local operator called the Hilbert transform. The solitary waves of this equation, they look more or less like this. This is decaying algebraically, and they look like they decay algebraically. They look like polynomial decay, essentially. And I just want to point out that if you compare with KDB, KDB is decaying exponentially. So this is like the difference between those two, which is nice. What is happening, probably a little bit of spoiler, is, sorry. What is happening is because of this operator for the Benjamin-Ono, this operator is not nice with the exponential decay. Like if you have a function that decays exponentially, this operator turns into something that decays polynomial. Right? So I just want to show you that solitary waves appears in different dispersive equations. So that's one thing to do research. I propose a model. So my first thing is, oh, there exist solitary waves, and then comes super difficult part. Is it unique? What happens if it's stable, it's unstable? Anyway, let me show you something really quick. There's also a different equation. You know, we mathematicians love to play with things, right? So we create a variable dispersion equation, which is called the fractional KDB equation, or depending on the parameter alpha, it's also called the dispersive generalized dispersion Benjamin-Ono equation, or something like that. And what you do is like you change your dispersion by something called the fractional Laplacian, which is also a singular integral. The fractional Laplacian is getting popular nowadays. It's also appearing in probability. Probability is a stochastic process. And this is the fractional Laplacian. And I love this thing because this is an example of something being non-local. Because to understand a derivative, you have to understand the function on the whole line, right? That it means to be non-local operator. Because when we teach Cal 1, you're always teaching like the derivative is local. It depends on the behavior around the point. And this is not local. So we put a fractional PDE there. Maybe just speed up a little bit. You got 10 minutes. Yeah, I'll finish it. What I just want to mention is that that's the solitary ways of those equations decay exponentially, polynomially that way. And this is a super nice paper when they prove this thing and also prove the uniqueness. So they're solitary waves. So as you notice, solitary waves are important for any dispersive PDE. And because of this polynomial decays, I'm probably closing right now because probably you are already tired of hearing me. We are recently doing some research, still on progress, with more collaborators to come, studying how the solutions decay. This is a work with Germán Fonseca, Guillermo Rodriguez, and we're doing research with, okay, the solitary wave decays polynomially. What can I say about the general behavior of a solution in weighted spaces, like decaying polynomial? And we have some nice results there, which I'm not gonna talk right now. Here are some references. If someone wants to ask me, I can share the slides, no problem. And there has to be a slide saying thank you very much. And it will appear.
You have any more questions? We go lunch. Right, please. Questions? Don't be shy. You can ask anything.
Yeah, that's one question. Can you comment a little bit more about the fractional Laplace? What is becoming popular in probability?
I hear because there are some process, Levy process. Probably here I'm not an expert. Some Levy process is appearing because think about it. Having one derivative is a lot. So if you have a Lipschitz, a Holder function, So the Holder function doesn't have, like, let's think a Holder function. You don't have a C1 derivative because it's Holder, right? But it has a fractional derivative, a derivative of order alpha. So in probability, you study things like fractional, like Holder spaces or things like that. So this is a nice way, because what you're using with the fraction is, I'm not asking you to be one derivative, just one half derivative. It's a nice way to measure regularity of functions without going up to C1 or C2 or C3 or integer derivatives. So those are processes when you don't have enough regularity. Essentially, that's the idea of fractional Laplacians. And I was meaning like the probably stochastic PDEs as well. But the question is good, so probably I need to double check.
Yeah, I got 2 questions. Will you go to the slide? The first slide where you were solving the KDB original equation?
When it's the sesh?
Yeah, I mean, in the like in the beginning of the presentation, where you were solving the KDB, like in the very, very beginning?
Okay, I'll try, but I don't know if the computer will.
Right there. Yes, boss.
Just make it that. Okay, please stop me.
No,
I think you passed already.
I passed already?
No,
Yeah.
It has like 3 graphs, a
3
yellow one, a
sections.
red, a blue, like.
That one. No, more. That one, no. Sorry, because those no.
There's more? There's more?
It's the sesh. It's the sesh.
Right, that's the one. So I got 2 questions. What was the meaning of the K? Sorry?
Oh, that it depends. It also looks like the translation, but also the height of the weight. Because the K here, the height. How high it is?
Okay, my question is, it's more a physics question. Like a physical one is, when you were talking about the solitons, from what I understood, I don't know if I'm correct, you didn't mention much about the medium, the way it's pretty much working. And as far as I remember from my physics class, like every wave needs some sort of medium to transport. Or so my question, it's more a physical question, and what's the role of the medium in the solutions? Because I don't see it.
Fantastic question. You assume that it's completely flat. I mean, there's no disturbance, like it's perfect. Like if you put like, I don't know, some obstacles on the bottom, I don't know if I understood your question, but if you put obstacles on the bottom, I don't know if there are solitary waves. I mean, you're very, I don't know if you remember the video I showed you, it's super specific, right? Like really shallow water. And the bottom was really like flat, completely flat, perfect.
But my question is like, you can have different mediums like water or sound. Does the medium affects the solitons? I mean, all of these examples were in
Maybe
water.
you don't have existence. Yeah, because you change the problem completely. Like from a mathematical, I will reply in a mathematical point of view. I assume that my domain is R. And that changes a lot. If I put an obstacle, like say from 0 to 100, yeah, I know if there's solitary waves there. And the people do that when they work like things like graph. You can have a graph, like thinking about different possibles the wave is moving. And in each of them, you can put like, an obstacle or something different. So what you do is like you put a solitary wave that you know and see what happens. Right? No, but yes, like here we're assuming super nice conditions.
All right, thank you.
No, super nice question.
Any other comments or questions? Okay.
So I guess for some of these questions, you can write a solution in terms of stochastic processes, right? Or no?
No, these are no, it depends if you add an stochastic term, like a noise.
Like the heat equation.
Like, yes, heat equation with noise. So you can take the KDB, you put a noise and try to solve it. What is interesting with this equation is because of Herman's question was really nice, because here everything is conserved. The mass is conserved. What I mean, like you start with the lump, and even though it turns into this radiation, the mass is the same. So you lost the height, but still the mass is the same. So you have something called mass conservation. When you put an stochastic term, that is lost.
No, but I mean, you can write the solution of the equation, like the heat equation, in terms of the semigroup of the Brownian motion.
Yeah, you have
the question is, if for these equations that are not linear dispersive, can you find stochastic processes and write the solutions in terms of
They feel like they stop to be stochastic. Like the Schrodinger equation, like when you look at like something that we call fundamental solution. Your fundamental solution of the heat equation is the Gaussian, which is an stochastic process. The fundamental solution of a dispersive PDE is something that is not even integrable. And I will explain you why really quick, because everyone wants to have lunch right now, I'm not talking a lot. And it's because of this. When the equation is dispersive, your solution is completely oscillatory. When you have in the heat equation, this turns into a k squared power times I, and then you multiply by I, and then you get the negative decaying of the function. So in dispersive, this is like completely oscillatory. So it's not an stochastic process, but it's similar because with Schrodinger equation, the fundamental solution is exactly, it looks like the stochastic, it looks like the same, like the Gaussian, the standard normal distribution, but it's complex value. So it doesn't integrate. So you use oscillatory. The equation is super nice because I can talk more. This is why we connect with something called harmonic analysis, because now we need to understand frequencies, because there's not something helping you. But now you need to understand how different frequencies interact and doing that. And through that, you introduce something called harmonic analysis tools. And that's what a connection that we need to use in this type of equation. So thank you for that.
Okay, any other last questions before we go? Okay, if there is no more question, we thank. Now we go for lunch and
Les van a los dos cursos, el curso de Miguel y el curso de Daniel. Hoy empiezan 15 minutos antes, por razones logísticas. Hoy empiezan 5:15 de Miguel y 6:30. Gracias.